Hi folks, and welcome to this module of the QLS 612. My name is Per, my pronouns are he and him, and I'm a postdoctoral researcher at the Neurodata Science Origami Lab here at MNI McGill. And today I would like to talk to you about reproducibility through shared computing environments. That is a short introduction to virtualization technologies. A few things before we're actually gonna start. To the folks with hearing impairments, you should be able to turn on closed captions via the CC button on the bottom right of the window that displays this video. If something doesn't work, please let us know via the communication channels or during the live session and we'll see how we can handle it. To the folks with vision impairments, all graphics, that is except those that have taken from publications, should be high in contrast and colorblind friendly. If there are any problems, please let me or us know in the chat or the other communication channels. To everyone, I will try my best to speak loud and clearly. If you have any troubles understanding me, please ask specific questions or to reiterate things during the live session, okay? If you feel uncomfortable doing this and asking questions via the public chat, please send me a direct message. Furthermore, I sincerely hope you feel comfortable indicating your pronouns during the live sessions. If so, please add them to your name if you want to. During the questions or discussions, during the live session basically, right? Please say your name as I, and I guess also others would like to avoid mispronouncing them. I try my best to present an objective overview. However, there is an inherent bias to such presentations based on personal opinions and experience. Thus, I'm looking forward to openly discussing every single point of comment with you all. And let's just all give our best to create an open, supportive, and welcoming atmosphere for everyone. Now, specific more to this lecture, talking about your objectives, your role, schedule, logistics, and maybe good to know things. So first of all, your objectives. You should hopefully gain skills, that is learn about open and reproducible methods and how to apply them using conda and Docker and or Singularity. You should hopefully know in the end the difference between virtualization techniques, and we hope to empower you with the tools and technologies to do reproducible, scalable, and efficient research. Furthermore, it would be great if you get involved, that is, familiar yourself with the virtualization and container ecosystem for scientific work, specifically your project, of course. Also, it would be great if you share, that is, bring everything you've learned here to your home institution and the lab and help others to also get into these technologies and use them. Your specific role, please ask questions during the live question and answer exercise sessions. Think quick and towards reproducibility because, of course, this is going to be our main topic here. And further familiarize yourself with the shell and non-graphical user interface applications that is basically building upon the things you learned during the bash module of this course. Maybe also start thinking about how you could apply or integrate these techniques that we're going to introduce here into your own research workflow. Hopefully, have a great time and give us feedback and help improve the materials. Our very optimistic schedule for this module looks like the following. First, we're going to have an introduction, including the problem statement, then talk about the different virtualization techniques, starting with Python virtualization using venv and conda, and then going a bit more in depth into containers. And in the end, we have a little section we would like to call the return of reproducibility. That is basically summarizing the things we've learned and putting it maybe a bit more into context. The logistics, and this more or less specifically refers to the live session that we're going to have later on, and your machine and your skills that you need for this. So your machine should be able to get Docker up and running and pull Docker images as well as virtualenv and conda installed. You should be able to work with the shell, which I guess after the bash lecture or module of this course should be possible. So, and during the live session, we're going to work with a few things, and this might result into 10 to 15 gigabytes of space on your disk, which no problem can be delayed at the end of the lecture. and talk to us if you don't have that much space or think you're running out of it, okay? And as I said many times before, please use the communication channels. So starting with the actual lecture now and the problem statement. Within the course repository you downloaded, you will find a script called fancy_tti_analysis.py, which is basically a modified version of a great tutorial from the DiPy docs, which is a Python module. It's just amazing. Has all the things you need and more for DWI or DTI analysis. And just imagine you starting a new project, coming to a new lab, and there's someone that did comparative analysis that you're also interested in and has this great analysis script that should be able to help you or run your data. So the colleague shares the script with you, which is going to basically be here, our fancy analysis.py script. Now, using the shell, navigate to the respective folder and run the script via this command. It's basically Python space fancy_analysis.py. And I'm just gonna quickly do that here. So this is my shell, just on my local machine. And for convenience reasons, I put the script, as you can see here, on my desktop. So I'm gonna cd into my desktop and run the script. And again, just imagine or pretend that this is a script your colleague shared with you to run a certain DTI analysis on new data for your project, right? This is quite often what you would have. Someone in the lab has something roughly comparable or maybe exactly what you want and should be helpful. And usually what people say is, oh, you just need to adapt it for your data or like that paths or whatever. So let's see if that's actually the case. Because in the end, if everything works, within the same directory, you should get several outputs. That is 3 PNG images and 1.trk file. And for me, like I got a warning, as you can see here, but no error. So hopefully, maybe things should be there. Let's check using ls. As you can see, I have the files I wanted to get out of this. That is 1, 2, 3 PNG images and 1.trk image. So for me, it worked. All good. The script I got from my colleague worked perfectly on my machine and most likely also my data. So no problem. But wait, the script doesn't run on your machine or maybe leads to different results. So what's the problem there? So what went wrong? So to get an overview of what might be the different sources of errors and problems here, let's gather some things. And for this course, it means just please write the errors down you got when trying to run the script so then we can discuss them during the live session and get back to it. Overall, what I could say now is something you might have heard before, and if not, will most likely hear in the future. It is, well, it works on my machine. As you saw, I got the images, I got the .trk file, no problems, only a slight warning, so it's all good. I shouldn't be worried, right? Works on my machine, so the problem must be on your end. But it's not as easy as that. Like the problem goes way, way deeper and spreads out, and is actually at the core of something we are facing and discussing in the world of science for a good while now. Actually, at least since 2013, where it became like on a bigger scope and like it became very public, and a great article about The Economist. But just to be sure, like all this started, like the entire discussion about reproducibility and this problem started way ahead of that as well. And there's a very great quote in this article that is modern scientists are doing too much trusting and not enough verifying to the detriment of the whole of science and of humanity. And what it means is that we just assume things work. We just assume things do the same no matter like where we want scripts, uh, like where we want analysis, the data, and all of these things. We just, in most cases, assume it does work and do not think further and actually evaluate if that's the case. And There's a great quote from Marley 2015 that brings us even further, saying that the broad adoption of computers in experimental science has both enabled and obscured research. And as I said before, code and analysis are predominantly just assumed to run reproducibly unstable across different machines, operating system, what have you, without being actually properly validated and tested. And this is especially problematic with increasing sample sizes and convoluted complex models. So there's, of course, the problem is always going to be there, but there is a huge difference between running, for example, a t-test and a group of, like a sample size of 20, or running huge linear mixed effect models on, let's say, 10,000 samples, right? So the problem very quickly scales to an extent where it's basically impossible to manage. And if you look throughout different disciplines of science, you see that it's a common problem, it's a common thing, because these days basically everyone depends on computers, IT things, infrastructures, whatever resources you have to do science. So for example, in economics, the same questions asked, right? Is it replicable? And then this article quotes usually not. Looking into cancer research, for example, studies from Bayer Healthcare found that only 14%, so 21, or only 14, that is 21% of results could be reproduced, and that 53 landmark studies out of those, only 6, that is 11%, could be reproduced. And thinking about what this research specifically is about, that is here cancer research, that is a major problem, right? Because you want these things to work reliably, robustly, and give the same results all the time, work very stable, because you will use those results and outcomes to derive, for example, treatment options. And going a bit further, there's a great summary, and all these things are adapted from Felix Schönroth, comparing different fields and the rough percentage of reproducibility in them, of results. So we, for example, have psychology, economy, cancer research, and experimental philosophy. And as you can see, there is a good amount of variation in reproducibility between all of these fields, with the red bars, the red color here, and percentages indicating the percentage of like unreproducible results. However, even though there's variation in them, it's always too much. It's too many results that cannot be reproduced. And as seen again, this is a common thing across different fields. So what's actually happening? And there might be a few options what might be going on there. Or unfortunately also intentional mistakes. We have the garden of forking paths for different analysis. We have questionable research practices and p-hacking, fraud, publication bias, and all of these, together with the adaptation of more like open science practices in the past decade, led to the number of retraction notices shot up tenfold, which is somewhat of an indicator here, right? So while all of these things are very important and interesting and should be discussed, like in this broad scope of things, we don't have time for that. And this is also not what we're going to focus on in the lecture, right? So we are going to be focusing on the unintentional, maybe sometimes if people want to do that, also intentional mistakes. Because talking about reproducibility and results, we actually have to define a 2x2 model with data and analysis as the main factor, where both can either be the same or different. So for example, if you use the same analysis on the same data, this is what we mean by reproducibility. If you use the same analysis on different data, means effects results are replicable. If you use a different analysis on the same data, results are robust. And if we use a different analysis on different data, results and outcomes are what we term generalizable. And there were a few very interesting methods and analysis approaches suggested throughout the last couple of years to investigate all these different aspects. For example, we have sensitivity and robust analysis, multiverse analysis, specification curves, vibration of effects, and ensemble approaches. So, and while we already talked about all the different fields and they all have the problems, we as neuroscientists or people who do neuroimaging might say, oh yeah, but like we are good, right? So we have no problems. And if you did some reading in the last couple of years, you know that this is not the case. There's all these different um, articles and research going on showing that we have a tremendous problem as any other scientific field out there. We see that certain analysis we assume to be robust were maybe including some bugs that render a lot of results basically with inflated false positive rates. Reproducibility of results in fMRI is heavily dependent on um, the different analysis approaches, stimuli task paradigms, all of these things. But it actually goes even further because as shown in this very nice study from Tristan and Goddard, which is doing also one of these courses here in this module, in this course. In 2015, did a study on reproducibility of neuroimaging analysis across operating systems. Because not only do all these different things I mentioned before matter and introduce a prominent difference, but even the operating system. And to address that, especially the operating system and the underlying what we call computing environment can introduce prominent differences, leading to diverging results, therefore interpretations and outcomes. And what he did here was basically running the same analysis on the same data, but across different operating systems. So for example, Mac, Mac OS, Windows, Ubuntu, as examples for operating systems there. What you can see is that there is a fair amount of differences in the mean absolute differences, t-statistics, random field theory, significance, and then going even further and computing dice coefficients, so the amount of spatial overlap between results. Ideally, everything should be one, right? Having the same exact outcome to the voxel level. But as you can see, this is just not the case, right? We have a good amount of variation in there. And this is obviously a problem because we don't know the ground truth. So which results should we trust? Which operating system, which computing environment is the one we should use? And therefore, it is important that we focus on a specific part of this 2x2 design here, which is basically the same analysis on the same data and therefore reproducibility. Because first of all, unfortunately, we don't have time to look into the others, and this is really where the operating system, the computing environment, comes into action, into effect. Because we talk about science reproducibility, that is each and every single project, and you have to be aware of that. In a lab, in an institute, big cluster, research clusters, all of these, that depend on complex software environments, consisting, for example, of the operating system, different drivers, software dependencies like Python or MATLAB, and other libraries you might have there. And basically the very, very rough outline, and please don't take this like a serious, like one word kind of thing here, but you have your operating system. On top of that, in that you have your libraries and binaries and applications. Right, and as you can see here, we have machine 1 and 2, and they might have the exact same operating system and applications installed, but the libraries and binaries could be different. And it could be that any of these parts change, any of these things that together compose the software environment, computing environment. And what we basically try to avoid is that things you might have heard before other people saying, that is the computer I used was shut down a year ago, I can rerun my analysis from an application. The analysis, for example, were run by my student and I have no idea where and how. And all of these things we try to avoid by focusing on cyber visibility with focus on software and computing environments. Because what you have there, if you change any aspect of these computing environments, operating system, libraries, binaries, applications, and whatnot, it's, for example, you introduce, or there are intrinsic numerical errors and instabilities. That is, errors may lead unstable functions towards distinct local minima, introducing certain problems regarding your outputs, variations, deviations. And there's prominent differences across the rest, where research has shown that the tensor stability relates to variability. So the more these things vary, right, or can vary, or are prone to be able to vary, the more likely your results deviate and the bigger the extent to which they deviate. So going back to the initial thing saying that it works on my machine, and I don't care, like I have no problem, it runs here, so you should see how this is going over there. We also have to talk about collaboration with your colleagues and everyone else when talking about science reproducibility, software, and computing environments, because sharing your code or using a repository might not be enough. I can already spoil it for you. It won't be enough due to the aforementioned reasons of all these different aspects of the computing environment changing and therefore introducing deviating results. So ideally, what we would like to have is that we have our machine 1, where our analysis runs perfectly fine, all good, and we would like to transfer it to a machine 2, where we basically share the application levels. However, machine 2 varies a bit in the library and binary level here, and therefore either our analysis don't run at all or lead to different results. And what we try to avoid is basically, well, I forgot to mention that you have to use Clang, GCC never worked for me, or I don't see any reason why it shouldn't work on Windows. And this actually means I have no idea about Windows, but I won't say. This is usually my go-to, but I'm honest, right? So I have no idea about Windows. But you might heard this before. And a lot of other things along this alley. Talking about central reproducibility also includes the freedom to experiment, because usually, quite often when you try to get a certain analysis to run, recreate or set up a dedicated computing environment, there's a fair chance that throughout the installation process, you will introduce a lot of problems and might actually destroy a fair amount of your existing computing environment if you don't pay close enough attention. Or maybe not destroy, but like vary it to a point where previously running analysis don't run anymore, and you have like incompatibility issues. Where this is a great example from XKCD, like an install script that tries to install a bunch of things, setting up an environment, and then quite often people say, oh yeah, if you encounter failures or something doesn't really work, it doesn't have anything, and all your old programs usually should work without problem. And what we try to avoid is basically, I just want to undo the last 5 hours of my lab work and life. And the basic thing, I don't know if you ever went through that, I certainly did at the beginning of my PhD. I'm trying to install a certain thing, maybe for the entire day. In the end, nothing worked, and I even basically rendered my previous computing environment unusable. So this is a real problem and danger, how you transfer computing environments, how to set them up, how to make them run your scripts. So are we all doomed to live in an unreproducible world, forced to painfully adapt and check every script we find? Well, maybe. However, You could also decide to learn to use what we call virtualization technologies. And virtualization technologies, what they aim to is first isolate the computing environment. That is, whatever your computing environment might be, including the operating system, libraries, binaries, and applications, you try to isolate them because second, you want to provide a mechanism to encapsulate these environments in a self-contained unit that can run everywhere. So basically, we reconstruct a computing environment, isolating it, encapsulating it in a form that can then be shared as efficiently computing environments throughout different machines and setups. So for example, we have our computing environment 1 and 2 running certain dedicated analysis. For example, this could all be our DTI analysis environment. And then we maybe have like a machine or deep learning environment. And what we want to do is isolate them, encapsulate them, so they are in their self-contained unit here, and then we can share them. So we can transfer them to, for example, a machine 3, which runs a different operating system, and maybe also different libraries, binaries, and applications. But we share them in a way that they were able to run on machine 3 and lead to the exact same outputs. This is central here. And thinking about the different dimensions of research, virtualization actually helps everyone. As rough dimensions, you could imagine projects and researchers. And throughout the scale, you could have single researchers in labs, and the project dimension, and students, the research dimension, and then it scales up to big research consortia like the UK Biobank, ABCD, Human Connectome Project, and other things you might know. In the project dimension and the research dimension, it's the PI. And as said before, virtualization helps in all of these instances and cases. Because what you would have in the project dimension is collaboration, workflow transfer, data set transfer, so in the end also reproducibility. And as said before and introduced, virtualization can help with all of these aspects because we can share computing environments. And the same basically happens in the researcher dimension, where it's about continuation of projects, building up or upon old projects with new data sets and different analysis variations. You got workflow transfer, dataset transfer, again, also reproducibility. So how does it actually look like in the wild? Virtualization technologies have three main types. Python virtualization, including, for example, veny and conda. Then we got what we call containers, like Docker and Singularity. And then what you might have heard and worked before, the virtual machines, for example, VirtualBox or VMware. And basically, you can think about these different types of virtualization situated on different levels of computing infrastructures and environments, where down here you get the bare metal installations, and up here you get the isolation in depth. So it ranges from what we call hypervisors, layers, virtual machines. You can see here are the containers, and the more you go to isolation in depth, you go to the application level, where just before we have virtual amps and conda. And what we're going to cover in this session is basically these aspects up to a container. This analysis in a dedicated Python environment, which would maybe not be possible with the environment using as a base, as a default, because it requires different libraries or maybe comparable libraries, but different versions of them. So instead of changing your default or base Python environment for good in terms of like making it run this DTI analysis, you could also create a dedicated Python environment, a Python computing environment specifically for this project, where you set up an entire new Python, new set of libraries, different versions, specifically dedicated for this TTI analysis and only this TTI analysis. And then maybe if you want to run statistical analysis later on these outputs, you could run it in the same environment, or if it doesn't work out in terms of dependency issues, just create another environment for that. Because in theory, you could have as many Python environments as you want. If you have 10 projects running in parallel, you could have 10 different Python environments for each of them. So that's pretty cool. And if you could use venv for that, as I said before, and conda, and venv, basically what it is, it's an environment manager starting for Python 3.4 and up, and it's usually pre-installed if you have Python running on the machine. And said before, it's command line interface. So to work with it in a terminal shell bash, you got to type Python, for example, space -m space venv to then work with this environment manager. So this is working, or what it does is it's creating these environments. But this is basically where it stops. If you want to go further, you got to use conda, which is an environment manager and a package manager for Python and even things beyond Python. So in addition to being able to create these environments and manage them, you can also use conda to install certain libraries, versions of libraries, and so forth, which is not possible with venv, where it would have to use another set of tools to do that. Again, it's also command line. It's in command line interface, so got to use the terminal again. For example, you can type which conda to find out the conda version and the installation path you're currently using. And if it's not installed in your machine, you can do that now, or at least before the live session, by following the install instructions that we put up on the course website. So now let's see if the mysterious venv might actually hold a key to enable our shared script. And we're going to put this old tale to the test, following best practices and creating a dedicated directory for all of our computing environments and Python projects. And for our venv attempt, this directory we're going to call moisture from. But as you can see here, we're just going to create a nicely nested structure within Galaxy, basically that will host all of our things we're going to do in this lecture and the live session. And then within Tatooine, this is going to be the directory where we're going to play around and test the Python virtualization things. So within that, we're going to use moisture farm as the directory file name for our virtualenv attempt. So using the shell, we're just going to start out with making our directory structure. So this is going to bring you back to the bash lecture, hopefully. So we'll start with Galaxy and then Tatooine. In Tatooine, we're going to create moisture farm. So just to be sure, everything is there. We see in Galaxy we have Tatooine, and in Tatooine we got moisture farm. So that's all good. Worked out. And now we're going to go into this newly created directory using cd. As you can see, again, have changed. We're now in this directory. And within this directory, we are going to create a new Python environment using venv functionality. And can't stress this enough, it's a command line program without a graphical user interface, and therefore it needs to be called within your shell. There might be certain graphical user interfaces that you could use to create Python environments, but overall it's definitely better if you learn how to do that using the command line interface, because certain resources and structure, for example, if you go to HPCs, there most likely won't be a graphical user interface. So if you know how to use command line interface, you're definitely on the safe side here. As mentioned before, the respective syntax is Python space -m space venv space, and then basically the name of your new Python environment. And you can call it whatever you want. Can you almost use every character and name, but usually providing a meaningful name is never a bad idea. And that being said, we're gonna call our environment C3PO. And I guess it's for you to decide if that's a meaningful or good name for what we do. So we're gonna write Python space -m space vn space C3PO. We're gonna hit enter, and we see nothing happens. We don't get an output here in shell, which is by default just what it is. So how can we check what happened? We can use ls to find out. So if we type ls in our current directory, we see we got a new directory named as our newly created Python environment C3PO. And within there, we're gonna have 3 directories. Just gonna show you that this is actually the case. I'm not making this up. We type ls C3PO, and we see we get bin, include lib, and some configuration files. But let's talk about the directories first. Bin, include, and lib, and here's what they entail. In bin, you got files that interact with the Python environment, the binaries. We got include, which are the C headers that compile the Python packages that you're going to use in this environment, and we get lib, the copy of the Python version along with side packages folder where each dependency is installed. So this will host all of the side packages, all of the things, the libraries in the specific versions you might want to employ within your Python environment. So, but how can you work with this newly created Python environment? As first, we have to what is called activate it by utilizing the activate.sa script, which within the bin directory. So if we just type source c3po/bin/activate, so we go into the folder that interact with the virtual environment, and I'm just gonna do that here. Type source c3po bin activate, and you can see what happens is instead of only having the base indicator here in front of in the beginning of my shell, which usually would tell me I'm in my base Python environment, it is now superseded by the C3PO environment. This is on first spot here, first place. And this is actually what happens. You're now, or we are now in our newly created Python environment, and it can use its resources to work with analysis and what you might want to do. And what actually happens, as indicated before, we put this new environment at the beginning of our shell's path variable, right? So what happens here, it's now in front of our base Python, our default Python environment, which is like fires up if you start up your shell. So now, as said, it's superseded by C3PO. So whatever we're going to use Python, we will use the C3PO environment versions of the things. And again, the change of the environment is indicated through the display of its name left to the command prompt. And this usually is only visible from the shell. And then you can use deactivate to, guess right, deactivate or leave our environment again. So if you just type deactivate, we see C3PO, the indicator here disappears from left of our command prompt, and we're now back using our base or default Python environment. Now that we have that, we could try to run our analysis again after activating our environment, and maybe also moving the analysis script for ease of use. But to keep that as maybe a motivation and not to spoil things that much, I'm not going to do this in this video here, but this is something we're going to do together during the live session. So there will be certain parts within this presentation where you might see some code and we might run portions of it, but large chunks of it I'm going to reserve for the live session so that we can go through all of these things together and try them out and see if it actually works. So without talking if this might work or not work, just ignoring it for a moment, we just gonna have a look at conda. So the other way of doing a Python virtualization. As before, we're gonna create a new directory for this part of our journey, and this time we call it Mos Eisley. So we're just gonna head out of our moisture farm directory using cd, and then ... going to one step up in our folder structure, and we're back in Tatooine, and we're gonna create the directory called Mos Eisley. So gonna make sure it's there. Yes, we got moisture farm and we got Mos Eisley. And now, as before, we're gonna cd into this directory, which currently is empty. Great. And while we used venv to create our virtual environment before, and then maybe later on use pip as a package manager, as said, because venv is only an environment manager but not a package manager, we can now use conda for both, as it combines the respective functionalities. And recreating our virtual environment from before, basically venv plus extra things, is actually very easy and straightforward using conda, with the general syntax being here now, conda space create space -n space indicating our name, followed by the Python version we want to use and the libraries we want to have there. We name again, name of our virtual environment, the Python versions, and the specific libraries. So, adapted to our mission making our detailed analysis script run, this would look as follows. When we're going to name our environment R2D2, we're going to install 3.7, and we're just going to assume we need parts of the classic Python stack for scientific computing. That is SciPy, NumPy, and Matplotlib. So going back to the shell, just gonna type conda create try-n our name R2D2, where with -y we're gonna indicate yes, I want to install all the things I need to create this environment, otherwise you would have to do this manually. Python equals 3.7, then we're gonna use SciPy, NumPy, and Matplotlib. We're gonna hit enter, and then we wait for a bit while conda does its thing. So it's collecting the package metadata. So basically the information it needs to create the environment we want to have. That is again a Python 3.7, which will include SciPy, NumPy, and Matplotlib. Depending on your machine and your internet connection, this might also take a while. So we just let it do its thing. Okay, it did it. Now it's solving our environment, which means it's going to find the combination of libraries and versions thereof that is actually possible to combine to create the environment we want. We see it's already doing a lot of things. And it's not only downloading Python, SciPy, NumPy, Matplotlib, but also a lot of other things that it needs to create the environment and make it work. And with that, we see our environment most likely was created. So how do we make sure? First of all, as we've seen, conda by default already installs a fair amount of library as compared to venv, because again, this is only venv is a environment manager but not a package manager. And now when we try to check our environment as we did before using ls, we see it's empty. There's nothing there. So what's going on? And this is part of a very important difference between venv and conda, which we'll check further now, like going on later. So we're gonna activate our newly created conda environment, and the steps or syntax are very similar to what we've done before using venv. Okay, so we're gonna use this syntax here, conda activate R2D2, whereas before we used vn, in version we used source, pointing it to the activate.sh script in the bin directory. Now it's a bit easier because we don't have to do like all the paths and whatnot, but just typing conda activate R2D2, as we've already seen, nicely pointed out by conda automatically here at the end of our package environment creation. So if we type that, press enter, we see base is now exchanged to R2D2. Okay, but under the hood, the same thing happens as with venv, that it's basically superseding our default Python environment. And now we're in our R2D2 Python computing environment. So first difference, as I said before, instead of using source and pointing to the activate.sh script, we can use conda specific comments because conda is actually its own program with its environment not being created at a specified directory as for venv. This was the big difference we were talking about a slide before, but within the conda installation at hand. So there is a dedicated conda installation which will also house all of the environments you're going to create and manage with conda. And you can actually check this via typing which Python. So now again, we are into our R2D2 environment. If we type which Python, we see this is now pointing to, in my case, users, my username on my machine, anaconda environments R2D2/bin/Python. So my conda installation is housed within the anaconda installation path here, and then we got our envs or environment folders, which will house again all the libraries, all the environments we're going to create and manage using the conda program. For you, this might be different depending on if you installed miniconda, anaconda, and again, of course, user-specific paths will also deviate. But starting from this point here and R2D2 bin Python, you should see the same things I do here. But it gets even better because again, conda has its own program, has its own specific comments. You can also use conda and list all the available environments that you have and can manage and interact with. And you can do that using conda info-envs. Type that, conda info-envs. And we're going to see a list with all the paths and names of our conda environments. As you can see here, I not only have the R2D2 one, but I have a couple of other ones that I'm currently using within projects. So for each of my projects, as said before as an example, I have a dedicated computing environment, a dedicated Python environment. So again, we're not going to try our conda environment to run the script. This will be reserved for the live session to keep you folks a bit pumped and hyped for that. But we definitely have some key points to remember going further. venv and pip, the combination of two, because venv is only an environment manager and pip being a package manager, can enable the creation and sharing of Python environments, including specific Python libraries and versions thereof. But to also share specific Python versions, specific builds, and maybe also build channels, you need to use conda. And the same holds true for certain non-pure Python dependencies. Conda in itself is already very powerful as it combines both the environment, comparable to venv, and package, comparable to pip managers. An important note we did not address in the slides, and also we can check that during the live session if you want. It's important to know that not all packages are installable via both conda and pip. So certain Python packages will only be available via conda, while others will only be available via pip. There is a certain amount that is installable by both, but overall, more packages are available through pip and less so through conda. And going further, please remember Python virtualization does not account for often required libraries and binaries on other levels beyond Python. Think about the little graphic we have of operating system, libraries, binaries, and applications, right? So try to always think about these different steps when thinking about virtualization. Because what we can do and what we're limited to is these aspects, these levels of virtualization, where conda already brings you a good way, good far amount there, but it's limited. It's limited right here. So to go one step further and creating more complex computing environments and maybe even operating systems, we have to look out for other things that are out there. And therefore, we'll try to use the next level of virtualization, which is containers, where a lot of folks say, and then of course also people working with containers, that this is actual virtualization, or at least it's more to the ground truth of virtualization than using Python-based or Python virtualization like conda and veny. So we're now talking about this specific layer here, containers, right hosted between virtual machines and the Python virtualization techniques. So in our 2x2 design, where we are right now in terms of interaction style and what we share our operating system, and containers actually could allow in principle both, because in the most like classic use case you would have the command line interface where you interact with your containers, but you can also host them on binder, for example. And in this case it's also important to maybe draw a distinction between these different options, because what we have, especially talking about virtual machines here and containers, is prominent differences in the way they work and the way they set up, as you can already see here. So we're going to compare virtual machines and containers. So virtual machines emulate the whole computer system, that is software and hardware. They run on top of a physical machine using a hypervisor, which you can see here. And hypervisor shares and manages the hardware of the host and executes the guest operating system. And guest machines are completely isolated and have dedicated resources. So, in other words, what you have is your host operating system running on your infrastructure, which could be your laptop, server system, or the cloud. Your host operating system could be Windows, could be Mac OS, could be a Linux-based system. You got your hypervisor layer, and on top of that, you build what you call a guest operating system, and you emulate the entire thing, right? So you got binaries, libraries, applications, all within these guest operating system that are independent from one another. So for example, if you run a Windows machine, you could have a Mac OS guest operating system, an Ubuntu one, maybe here, and another Linux one, like a Mint operating system housed in here. And because you got to emulate all these things and all these different aspects and components, virtual machines tend to be very heavy. They're going to be large in size, and they're going to be comparably slow, because they work in a way where, again, everything is emulated. So there's only so many resources you have that you can emulate and share. In contrast, talking about containers, they share the host system's kernel with other containers. That is what it's called a kernel level virtualization, where each container gets its own isolated user space, and only bins and libs of binaries and libraries are created from scratch. Therefore, containers are very lightweight and fast to set up. So as you can see here, again, we have our infrastructure, which could be, again, a laptop, HPC, cloud-based systems. We got our operating system, Windows, Mac OS, Linux-based, and then we got the Docker engine, and within the Docker engine, it's actually important to say this, that if you run it on Windows and macOS, within this engine here, there's actually also, or before it is, like also the hypervisor layer involved a bit. So, and then instead of creating and emulating the entire software and hardware within these independent guest operating systems, you only create virus libraries, and on top of that, the applications. And that's why the containers are comparably lightweight. They tend to be way smaller than virtual machines and way faster to set up because they're directly assessing your host systems resources. I do not have to emulate entire new things. And in this lecture, we're going to focus on Docker as a virtualization and container software because it's just it's easier. It's easier to run across different systems, especially operating systems and machines, and set up. And therefore, we're going to use that, and we're going to go into a bit of difference with other virtualization systems soon. Just as a reminder, here a container is a closed environment and will use the exact same software version drivers independent from the system it runs on, right? Because it will use your resources, but it will create binaries, libraries, and applications on top of that. As you can see here, we got operating systems, then we're going to create, using containers, our libraries, binaries, and applications. So these computing environments, 1 and 2, could be 2 containers, 2 virtualized computing environments. We isolate, encapsulate, and share via container technologies. Docker is the leading software container platform, and it's actually an open source project and runs on basically all the operating systems, Linux, macOS, and Windows. Where, important notes here, I have to be honest, it runs best on Linux, followed by Mac OS X, and then Windows. It's possible to run it on all of them, but getting it to run on Windows in a certain way can be a hassle. But our installation structure on the course website and the live session should be able to get you there and run these things. And now, addressing the aforementioned comparison with other virtualization technologies. First of all, the 2 most heavily used ones are definitely Docker and Singularity. And we're not going to use Singularity here because basically it does not run natively on Mac OS X and Windows machines. So what we'd have to do to use Singularity on these machines is actually use another virtual machine, and then within that run Singularity. So that kind of defeats the purpose here a bit. So we therefore focus on Docker. To nonetheless talk about both of them and draw the important distinction and make sure you all have an idea what it's about, Docker has a certain problem with escalating privileges because efficiently you need to be treated as a root on the host system. And of course, this is usually not supported by administrators from HPC centers. So if your lab, your institute, university uses HPC centers for heavy computations, they will never allow Docker. Because again, you need to be treated as root efficiently on this computing resources to be able to run Docker. And if you allow users this kind of access, you can basically count the seconds till something goes very, very wrong. So instead of Docker, these resources use Singularity, which is a container solution created for scientific and application-driven workloads supporting existing and traditional HPC resources. Because, and here, this is the really important difference, a user inside a Singularity container is the same user as outside the container. So once set up, people, like users on the resource, don't need to be efficiently treated as root on the host system. You can just run the container and work with them. And this is why HPCs support Singularity, but not Docker. However, if there is a Docker container out there you would like to use on an HPC, you can actually use Singularity to download, convert, and run existing Docker containers with ease. So that's pretty cool. And to bring that for you in context, most likely what you will work on or what you use for your work and what we're also going to talk about in a different module of this course is Compute Canada, where again, do not even think about using Docker. It's just not there, and most likely it will never will be. But there's definitely Singularity you can use. So within the things we're going to talk about here, a lot of them are transferable to Singularity, and important differences are outlined at the end of the presentation. So once more, going back to our different computing environments with the operating system, libraries, and applications. The idea with Docker and Singularity, other container versions, is that we, again, can't stress this enough, recreate, encapsulate, and share these computing environments. For example, we have one Docker file, one computing environment, a container that runs a bash script, one that runs a Python script, and one that runs an R script. And the way to set up and through the existing infrastructures out there, for example, also GitHub and other things, it's actually possible to apply them or use them, manage them within the continuous integration server, where your computing environment will be built, tested, and version controlled. Then you send them on Docker Hub, which you're going to talk about in a second, and then people can use them on their local machines, can be a laptop, can be a desktop machine, and via converting them to Singularity also on HPC. So this is the idea. Creating our computing environment, encapsulate it in a way we can share it. All of them usually have a dedicated purpose. We share them online and then people can use them. So where is Docker? Think about our 2x2 design again. Docker is command line based, so it does not have a graphical user interface. On Unix-based operating systems, for example, Ubuntu, macOS, you can open a terminal and type Docker to test if it's there. Just type Docker, and we see, oh, a lot of things happen. This is what we call the Docker man page or the manual page, basically giving you an idea about, first of all, it's telling you Docker is installed on your machine, and it's giving you the different options, how to run it, different comments, and all of these things there. On Windows, it heavily depends on the specific Windows version you have. So it might either be the Docker toolbox, the Docker engine, or if you have the Windows subsystem for Linux, open that and do the same thing, type Docker, and you should see the same man page. Once more, we got our installation instructions on the course website, so make sure to follow them precisely on the point. And if some problems appear and you cannot solve them by yourself, just let us know. As you saw, there's a lot you can do with Docker. But before we can go in the depths of the Docker galaxy, we got to make sure it actually works. Right now, we know we can run the Docker command, but we cannot be sure that Docker itself actually runs. And to do that, we're just going to type docker run hello world and press enter. And what you see is like a few things happen here. First of all, we see some things are being downloaded, and then we got like an output message here and some further information. So what's actually happening? This command, docker run hello world, tells Docker, the program, to run or execute the container hello world. So this is Docker command, docker run, execute a certain container, and this is the name of our container. And if the container we want to run is not already downloaded and installed on our machine, Docker automatically searches for and downloads it. So this is what you see here in this part of the comment. Up here. You see, oh, it's unable to find the image locally, therefore it searches for it, pulling it from an online resource, tells us the pull is complete. We get the share for it and the status that the download is completed. And then Docker runs or executes this given container, doing whatever the container is supposed to do. And here, this is a container called Hello World, which task or aim is to check if our Docker installation works as expected. And you can see we get a nice message here, hello from Docker. This message shows that your installation appears to be working correctly. Nice. And then we get a bit more information what Docker, our program, did to make sure that the program is actually working on our machine. You can check that out on your local installation. And as said before, going back, sorry, to this graphic here, we're gonna share images. Usually, it's good and intended to be shared online via this thing called Docker Hub. As you can see here, it was automatically downloaded from an online instance. And this Docker Hub is what you might call a very special place in the galaxy. In most cases, Docker images are stored at a certain dedicated place from which they're also downloaded. Can be in light speed, but that depends on your network. And this mysterious place is this thing called Docker Hub. And it contains an amazing and huge online repository where folks, you included, can just upload and store as many Docker images as they want for free so far. Most likely that whole system on Docker Hub and the software will change in the future because of more demand, but so far you can upload and store as many images as you want. The only requirement you need is a Docker ID, so an account on the Docker Hub, which doesn't cost you anything on the free plan. And then you can download, upload images. And as you can see, it's really working. If you work with MRI data, usually, or ever at all, you might have heard about the fMRI prep container. It's what we call a BitSap. It's a containerized workflow dedicated to do standardized pre-processing of MRI images, MRI data sets. As you can see here, on its Docker Hub instance, its Docker Hub profile repo, and you can see it's been downloaded over 100,000 times. So, of course, not all of these downloads will use fMRI prep for their analysis, but a good amount of them will be. So, and this is just an example. There are many other images that have been downloaded thousands and thousands of times. So, creating these shareable computing environments is definitely something that is already heavily used in the open in research workflows. And once you have built your own little image and you can you tag them, this is things we're going to go for later, you can actually just push them to Docker Hub via the command line again, just Docker push in the name of your image, and it's going to be uploaded and made available there. However, you can also automatically build from a GitHub repository and pushing commits to a respective repo that includes your Docker image will automatically update and build your image on Docker Hub. Unfortunately, this recently changed to be only possible via paid plans, but you can also apply for an open source like free build plan on Docker Hub directly, so this works. And this is really cool because you can and actually should combine virtualization and version control. Bring in Git, GitHub, the things you've heard about before, in another module of this course, and Docker, so virtualization together. So now let's further explore our Docker commands within a typical workflow. At first, we want to download a certain Docker container to work with. For the sake of simplicity and time, we're going to use a very classic Ubuntu container, so a Linux distribution. Instead of automatically downloading a container via Docker run, we will use the respective Docker command, which is Docker pull. So basically, if you want to download an image, all you got to do is write docker pull and then the image name. For us, this would mean docker pull Ubuntu. So let's run that on our local machine. Docker pull and then Ubuntu. And comparable to Hello World before, we see it's not on our local machine. So it's going to be downloaded from this repository. We see our pull is complete and download finished. Got our shot. Everything's good. It's there. And what you can see if you spend a little closer look there is we download all the layers, what is called, that are needed to build the classic Ubuntu Docker container. And with the message status download new image for Ubuntu latest, showing you that everything worked. So basically, these things here, these arbitrary number and letter combinations, and then pull complete, that's basically a layer, a certain part of your computing environment, and all of these different aspects are needed to, in the end, create your dedicated, the intended, wanted computing environment. And you can check the existing Docker images on your machine just using the docker space images command. So if we type docker images, I'm just gonna increase my shell a bit to the side. We see we got our Hello World container. We just downloaded a wee bit back there, and we got our Ubuntu container we just downloaded. And what you get there is the repository name, their tag, their image ID, their build, and the size of all the Docker images available on your machine. So going back to this output again, we got the tag, the name, the image ID, we got a repository, the tag, the image ID, the when it was created, and the size of it. And as you can see, Hello World is just like a few kilobytes. And to run a very basic Ubuntu container, all we need is 72.8 megabytes to make it run, which is incredibly small. Some super important note here. By default, Docker pulls always searches and downloads the image that is tagged with latest. And this basically defines a certain version of the image. Hence, if you want to have a certain different version, for example, an older release or a new development version that is not yet made it into a stable release, it is necessary to indicate the respective tag. So you can do a docker pull, your image or container name, and then followed by a colon and the version. And to show you that in action, we see here, the first thing we see when we type docker pull in Ubuntu without specifying any text or version is the message using default tag colon latest. Again, by default, we always get the latest version of the image out there, which of course might be problematic if certain components of the computing environment change between versions. If you just use the latest version all the time, however, things are changing between releases and versions, for example, from version 1 to version 2, then reproducibility is, of course, not on the table anymore. So always make sure to get the certain version, the dedicated version you want to run, because that will also guarantee that, for example, if you put it into your manuscript saying that, oh, I used this Docker image with this version, that people can use the same version to maybe rerun results or apply your things, your analysis to new data. And from this first introduction, a few key points to remember. The host machine's kernel is shared between the containers, which, what we not talked about before, could be problematic. So in a sense, it's very good because we share share the kernel. It's kernel level virtualization, so therefore we don't have to emulate all these things. Containers are very lightweight and faster than virtual machines, but depending how it's set up and what exactly you do within containers, this can reintroduce external dependencies from your host system into your Docker image. And we're just going to talk about more about these things in the live session. If you want to use containers on the HPC side of things, you got to use Singularity. Both Docker and Singularity don't have a graphical user interface, and Docker and Singularity images can be hosted for free on the respective Docker or Singularity hubs. By default, both Docker and Singularity will always pull the latest tagged images, which is both good and bad, because in one sense you don't have to worry about it, it will automatically search for it and download it, but specific tags but versions are needed if you talk about reproducibility, which is our entire thing here. So always, again, make sure to download dedicated specific versions. Docker and Singularity images are composed of layers which can be shared between images and can contain entire operating systems. Remember our Docker pull, Ubuntu, as you see here. This is our layer. This is the layer we needed to download to run to make the entire Ubuntu operating system in its minimal version happening here. And because these layers, so if we want to download another image, another container that also uses Ubuntu, this layer can be shared, and therefore containers can be more lightweight because the heavy load in terms of storage and layers can be shared, and different images can utilize the same layers basically. Okay, so after having heard about a bit of the basics of images and see how we can download them, how we can check out what image we have, now the question is really, the next question would really be, how can we work with them? Like, what can we do? And let's assume we just want to use our just recently downloaded Ubuntu image. We want to what is called run or execute it via the docker run command. And remember, we have seen that before with the hello world. We actually already did run a container and to check if our installation works. And now we're going to basically use this new Ubuntu image we just downloaded and want to work with that and run as well. So we see we have it here, should be ready to go. We type docker run and Ubuntu. And what happens? Nothing. Docker used run, nothing happened. So all the fuss with that, all the countless slides and talk about reproducibility and whatnot concerning virtualization and containers, and all the fuss really for that, nothing happens. What's the problem? What's going on here? The thing is, and this is very important to remember, each Docker image is built for a specific reason and purpose. Hence, what happens when you run a given Docker container depends more or less exclusively on setup and definition. So that's why it's also like outlined here in this box. Please remember that always. Images can and most likely will have a dedicated functionality, or depending on how they set up, can also be utilized more broadly. And the current image we are using has no defined mission, it has no task, its functionality, like there's no thing that should automatically start when running that image and container. It is therefore always super important to consult the README or documentation of a given Docker image or any container before using it. So make sure you are aware of the dedicated functionality or the way it works when you start it up running. And the key point here is that the automated functionality poses as one major approach to use Docker images, for example, within pipelines and workflows, but maybe more to that later. It's also possible to define tasks during initiate of a container. And for this, please try to remember the way Docker or other containers work and how to set up in terms of how are they situated between your host, operating system infrastructure, and the things that they do. So, for example, we would like to task our Ubuntu container to tell us hello from within your container. Just a nice greeting message, because these days you definitely get not enough of those. So we type docker run ubuntu echo hello from within your container, and we press enter, and what we get is hello from within your container. It doesn't seem like a lot right now. I know, like that's comparably no fuss to what we've seen before, where nothing happened. What's the key? What's the real thing here right now? What is what we should take away from this and what we need to learn? You might not be aware of it, but this message, this hello from within your container, did not come from your machine, not from your laptop, desktop, whatever you're currently using or during the live session will use. It will come, and it comes from a different realm within your machine, the Docker realm. Again, think about how these things work and set up and are situated. The docker run ubuntu command will be executed and run within your machine. However, the task, the echo hello from within your container, this message will come from within the realm of the container, of the image. So if we go back to our output here, we get our task, and then the next line we get hello from within your container. And this message here, this output, is not coming from your host machine. This comes from within the Docker realm, your container. Okay, this is the important part here. We gave it a task and it did something. And the task was executed within a computing environment that is different than your host system. However, if the force allows, and usually does, you can also enter this realm utilizing a given Docker container within what we call an interactive fashion, which can be achieved through the including -it flag within the docker run command. So we're going to change our docker run ubuntu command to docker run -it ubuntu. Before docker run, but then -it ubuntu. So what happens now is not nothing, but we see a completely new command prompt indicating root, add arbitrary number letter combinations. Get our command prompt. We are definitely somewhere else. We left the realm of our host system, of our host machine, in my case, my laptop here. We are not here anymore, we are somewhere else. We are now inside the Ubuntu Docker container, and we can utilize the functionality from the present Ubuntu operating system we are in. And yeah, you're basically using an entirely different new machine. Just, for example, checking the output of ls, where before we should have gotten the info about whatever is in most likely. If we type ls now, we see the classic root directory trees and a folder structure of an Ubuntu system. You can see we are now in a completely different operating system inside the Ubuntu container, this new realm. We are not inside our machine anymore. And now we could start to interact with these files here, run certain things, and all of that would be done in the Ubuntu container image and not our host machine. And we can leave this realm, we can close down our container again just by typing exit and press enter. And we can see we are back in our machine. Depending on a given image architecture and definition, it should remove herself from what we call running instances when exiting. However, to be sure, it's worth to ensure that and check running instances when you notice, for example, a drop in performance. Really, really important. Make sure to check resource allocation and uses of image you work with. Because some images might need more gigabytes of RAM, they might need more CPU than they have by default. And you can change and set these things, for example, within the given run command, or also as a default. And we're going to also do that within the live session on your machines. And just to be sure you grasp what's going on here, what's meant by that, if you type docker ps, what you get is a list of, again, container d image commands, created status ports and names. So this sorry, will basically tell you, are there any Docker images, any guest operating systems, computing environments running in the background? And basically, which ones? If so, what's the command that's currently running when the image was created, the current status, and maybe ports, so like other resources they are using. Chances are, if the container, the image is set up in a way that does not remove itself upon exiting, that these containers and the computing environments will run in the background, and it will just use more, like they will just block some of your resources. So if there's maybe like some like command running in the background that uses 10 gigabytes of RAM, could be, and your computer has 16 gigabytes of RAM, then those 10 gigabytes of RAM will not be available for whatever you do on your machine, will be gone. So if you really notice a drop in performance or maybe storage, make sure to check Docker PS and any potential images that might be running in the background. You could even do some real-time trouble though, but roughly, no it's not, but it sounds cool. If you add the -a to the Docker PS command, you actually see a list of all the different images and the comments you run in the past. So here we see like our hello world, our different initiations of the Ubuntu image, the comment we ran, when it was done, the status, if they were exited, if they delay any ports, and their arbitrary names. So if you notice some strange behavior or just want to make sure what was happening a while back, you can use this -a extension, the Docker PS command, to evaluate previous run instances. So now let's go back to our main goal, to just not lose track here, because I know it's been a while. We want to make our analysis run everywhere in a reproducible manner. So it's still about our DTI analysis. We checked vny and conda before, now we're in containers, and we want to do that. So the first thing we might want to do in this new kind of mission here is we want to go into the Docker realm and create some new files, some new folders to maybe start working on this problem and the analysis. So as learned before, we are going to go into or start up the container or image, our Ubuntu image, using docker run -it, and this is a new thing here I spelled in there. It's --rm, which basically adds the functionality called remove from running instances. So if you always want to be sure images are removed, the thing we talked about in the previous slide, you can add the --rm to your docker run instantiation. So we're going to do that, docker run -it --rm and Ubuntu. And we are back in our Ubuntu image. Our container is up and running, and we can interact with its resources. So we're going to start with creating a new folder called defeat unreproducibility empire. Make directory defeat unreproducibility empire. We use ls to check it's there. Here we go. It was created in our image. And let's imagine we spend the next 6 years and roughly $76.5 million on this project, making it run, creating a reproducible computing environment that can run our fancy DTI analysis. We made it happen. It runs in our container. Let's just assume that for a moment. Having achieved the galactic reproducibility piece, we decide to exit the realm, spend a little time off. 16 years later, as well as the sell to Disney of our computing instance, we decide to return and have a second look on our analysis and computing environment. So what we do, we spend a lot of time here, create a bunch of files and whatnot. We made it happen. We are done. We exit our container, spend some time off, and then we are intrigued again. I just wanted maybe to run it again, maybe extend it also. We go back into our container and make sure we check our files again using ls. But what do we see? What happened? Our defeat unreproducible empire folder that holds the key, the solution to reproducible analysis of our fancy DTI approaches is gone. It disappeared. It's no longer there. It's the Phantom Docker? Maybe. Our project folder and everything in it disappeared from the Docker realm. It's gone. It's just gone. It's gone so. And the reason why that is that when working within a Docker container, creating, modifying, and deleting files, these changes are neither permanent nor saved. And this is against the encapsulation and reproducibility idea. That means if you run a Docker container, work with files within that container, spend years and years, for example, making that DTI analysis happen and whatnot, the moment you exit the container shuts down and is removed from running instances. All your changes, all your work will be gone. It's not possible ever to get it back. Because if it would be possible to change a given container, a running container, modifying it, deleting files, adding things, and then exiting it would be saved in that state, then this would be a new instance of this image. It wouldn't be the same computing environment anymore. And this is, of course, against encapsulation and reproducibility, because this is all we want to do, right? We want to encapsulate an environment and share it to make things reproducible. But if we were to allow it to change things on the fly, then all of this wouldn't matter, because it won't be the same image and won't be reproducible in most cases. The other thing is we cannot interact with the data stored on our host machine or somewhere outside the container Docker realm. So if I'm now inside the container and would like to copy, for example, all the hard work I did to my container and just did it as we done here, there's no way, no chance we do that, because the Docker realm and our host machine realm are closed. It's encapsulated, it's packed in the container. So there's no door in and out at this moment. So this also won't help us. In order to address both of these problems, so creating, modifying, deleting files, sharing data between our host machine and the image, we need to create fancy, I'm just renaming fancy here, force bridge, but it's actually not, between these realms. In other words, we have to mount paths between the host machine, our local laptop or desktop computer or what have you, and the Docker container, the image, which means or describes a mapping from paths outside the Docker container to paths inside the Docker container. And this is achieved through the -v flag within the docker ran command, and utilizes as follows. You write -v and then path outside the container, path inside container. Where on an example, applicated here, you see this path here is basically the path of something, a file or a folder on your host machine, on your local machine that you want to make available inside the container. This is how it works. So for example, we could create a directory called hof and within our Galaxy folder and make it available inside the Docker container as the folder called rebelbase. So let's do that. First, we're going to exit because this comment won't help us here. We didn't include the -v flag. And make that a bit smaller here. There we go. So first of all, we're just gonna ascend a bit here back to our Galaxy folder and now make the directory called off. And see, we don't need to cd in that, but we could just for good measure. We're now in there, we see nothing is there. And then we do our Docker run again with the -it flag for interactive use, --rm for remove from running instances upon exiting, and now the -v flag where we mount the newly created directory, as you can see here, colon 2-rebel base inside our Ubuntu container. This is how you would do it. You can use absolute paths or relative paths. However, I would strongly recommend using absolute paths just to be on the safe side of things. And then running our Ubuntu image again. So nothing changed as compared before. So there we are back as root within our container. So if we now create a file within the directory rebelbase, it should magically appear on our host machine within the host directory through the mounted path. Because at this point in time, these two paths, outside and inside the image, are identical. We mounted them. So if you go back here, first of all, we can make sure that rebelbase exists. Right now it won't be here in our root, so we have to make sure. You can see here, use the initial slash, and then we see it's there. It's currently empty. So using touch, we're going to create a file in that directory called devstore plans, and it's going to be a PNG file. We do that, and we verify it's there using ls. Yes, our newly created file is there. So how can we now make sure it's actually inside our host machine, that it appears, that it works, that we, within our Docker realm, within the image, we created a file that we can now actually use even upon exiting container, because we did a mounting of paths and therefore made it available. For that, I'm just going to open a new shell. Just going to increase size a bit here so you all are able to see what's going on. So while within this shell we are inside the container, the Ubuntu image, within this shell here we are on my local machine, my laptop. So if this whole thing worked and these paths were really mounted, then within my username, desktop, Galaxy Hub, I should have this file, devstore plans. So let's check that out. And we see it's actually there. We did not create it on my local machine. We created it in the container, but through the mount, it was saved and created on my host machine, therefore made available to me for working with it, which is fantastic, which is what we want. Because quite often, we want to work with images and we have data input and output flow, because you don't want to, I mean, you can include data into a container, but it's not really the preferred way to do things. The cool part is that you can even restrict the rates of mounted paths, for example, to read-only in cases modifications should be printed, so that you don't accidentally destroy your entire analysis pipeline or delete data or what have you. So if we do the same thing as before, but adding this little piece here, colon RO, so colon read only, this mounted path here is gonna be read only. Oh, sorry, close that by accident. There we go. So we exit here. We go back into the container using our old command, adding colon -RO, therefore restricting access right to be read-only. We're back here, and we now want to remove this newly created file in the rebel-based directory. We get the message cannot remove this file because it's a read-only file system. And this really comes in super handy if you basically have an input stream of data and an output stream, and the input stream should not, like the input data stream should not be able to by accident delete any files here, which could happen if you don't pay close attention to the automated functionality or the way you mount it paths or where you do things using the shell. So this is really, really handy and an important functionality. And as I said before, most of the time it's a good idea to indicate absolute paths on the host machine. As our example, the -rebel base didn't exist before mounting it in the Docker image. It was automatically created. However, this can also be a problem because it depends on the Docker image what is there and what's not there. It set up a definition. So for example, there could have been a folder in the same path, same name. For example, with an automatic functionality, a certain directory can be expected. So always make sure to check expected paths and amounts of images you work with. Because if what can happen is if you are mounting something or mounting it to a folder that already exists and like dedicated in that way, it's possible to overwrite. And this is actually what happened. The existing directory within the container will be overwritten through the directory specified during the mount. So for example, if a directory called rebel base would have existed within our example, the specified mount we did would automatically have overwritten that rebel base and all its included files without even telling us. Because this is just how Docker works in this sense. It will create that mounted path and it will just overwrite whatever is already there in the same place. So this can become a problem if this directory, for example, stores important data or certain aspects of your analysis pipeline or what have you. And as usual, make sure to check the README and docs of a given Docker image or other containers. Another important note, you can mount as many directories and files as you want, indicating each with a -v flag. So for example, you could map, as said before, an input and an output stream regarding your analysis to your Docker image or the image you want to use. So for example, you want to do pre-processing, analyzing data, you have one dedicated input directory that you mount as read-only to prevent the overwriting or alteration of raw data, and you have a dedicated output directory where you want to store results and outcomes of whatever you do your analysis. And it's basically looking like that. You see, like for each path, we have one specific -v mount here. Going back to our container, let's exit again. Then we just run that docker run -it -rm, starting with the first the username desktop Galaxy. We mount that to rebel base as before, making sure it's read only, and then we do the next one, which is going to be our output directory. X-Wing, and within, of course, our Ubuntu image. See, we go back in our container using ls. We see our home, like our root directory structure folders, and we see Rebel base, and we see X-Wing. Again, if we want to do something with Rebel base, this should not be possible because it's a read-only file system. Therefore, it's Rebel base, and we want to do a new file, dev star plans updated PNG. We can also not do that, right? Because it's read-only, so also not saving files is also not possible. So if we do some new analysis and have some new outcomes from our input directory or the data, if we're in there, we want to save it to be made available later in a dedicated different directory, we have to change paths. So we have to go to the X-Wing directory, which we mounted here as our in the forward output directory, not restricting access right. It's dev star plans updated PNG, and we see no error message. And getting our other shell on my host system back, checking desktop, Galaxy, and the Dagobah directory now, we see we got our updated files in there, our outputs of the analysis. How you might want to think about it. Again, also make sure to check the readme and docs of the container image you use, because some paths and or files are expected, and if these paths are generated automatically, and what you have to take care of here. Key points to remember from this section would definitely be Docker and Singularity images usually have specific purposes, and for examples for this are automated functionality and interactive usage. Running instances of images need to be checked, and images can never be changed. And this, of course, is a potential problem, as change results from a running container cannot be preserved without mounting paths or recreating and updating the image to make it a new instance. Good and bad, as many things with these technologies, because everything needs to be thought through before running certain things. There will definitely be a steep learning curve once you start working with these tools, and in the beginning there will be, of course, frustration because you forgot to mount a path or maybe mount it in the wrong way, and then your work is basically gone, and you have no way of getting it back, so you have to either update the image or really make sure to think everything through before like running the container, so to get data in and out and what have you. The Docker and Singularity realm and your host machine's realm are two separate places. They must be connected through a mount if you need to provide a flow of data. Otherwise, not possible. Okay, so far we hopefully learned at the Docker Academy how Docker and also, of course, other virtualization technologies work, how in this specific case we can download, use, and manage images. However, we still have a pressing question to answer. That is, how are Docker images and other images, for example, Singularity, are actually created for specific projects, pipelines, what have you. For example, our DTI analysis. Well, the question there is then, how are different programs installed, and how are locally created images, once you have them, shared with other people? And when it comes to creating Docker and other images and containers, there are two essential parts that are relevant. First of all, it's what is called a Docker file, or in case of Singularity, a recipe. That is basically a recipe that defines all the different ingredients, components of your computing environment that you want to recreate, encapsulate, and share. So for example, if you have two different images you want to create, for each of them you would have here a Docker file that basically contains a mixture of Docker specific images and commands, like the from Ubuntu here, which basically specify that we want to start from an Ubuntu image as a base and build upon that. And then it basically follows classics Linux-based operating system syntax and commands. For example, to install programs, you would use apt-get install x and here in Dockerfile 1 and y there. So based on that, you would just specify all the different things you want, installation instructions in that file, and then the second essential part comes in, the build command. Here, the Docker build command that you would then point towards a specific file, and which would then use all of these different instructions in there to recreate, encapsulate your computing environment in a way that can be shared. So for example, here are by now well-known computing environments 1 and 2 with the same basic or base operating system, different libraries and binaries, but then again, the same applications. So this is what's needed: a Docker file or a singular recipe and the respective build commands. So instead of going through all of these things together with you now within this video lecture, I decided, comparable to the veny and conda parts, to reserve that and actually building our images and testing if our analysis works, because we still don't know how to make that happen, right? Our goal is still to make the analysis run on everyone's machine. We will do that during the live session, so we will not go through that here. However, the slide version, that is the PDF version of this presentation, will have all the specific comments and steps to guide you through so you can use them during the live session and to follow up there. So again, instead of going through this entire process, we're going to keep it with the teaser here. We need a Docker file or a recipe and the build command, and check everything else out and actually do it during the live session. And so now I'm going to jump right into important key points to remember. Thinking back a bit about the entire mounting path situation and aspects we talked about there, always remember that a given image can never be changed. If you need to change an image, do alterations in them. It's necessary to recreate and build an essentially new image. For example, in case functionality is missing or things need to be adapted. Because otherwise, this would go against the idea of reusability and encapsulation, because changing functionality or adapting them, adding files or what have you, would efficiently change the computing environment. Therefore, things are most likely not reproducible anymore, or at least to a different extent. There are two important things are essential for building images: the build file and the build command. And as we saw during the download of the images way back, images are composed of different layers, and the build process actually mirrors this and follows the respective principles while adding the different components and functionality that we specify within the build files. And as I said before, they basically mimic setup of Linux systems and contain a mixture of Docker Singularity and Linux commands. It's possible to share layers between these images, which can then speed up the build process and minimize storage. So this goes back to managing containers and the usage resource usage as compared to virtual machines, which tend to be heavier and require more storage space if you have like multiple of them. The creation of build files and images is definitely a learning process with a steep curve that is very convoluted, prone to errors, but please always keep in mind that the benefits can be tremendous, saving you countless hours of installation, addressing usability-related problems, or what have you. So the benefits definitely outweigh the costs in the beginning. Even if it takes you a week or two to get into it and actually make it work, the amount of time you will save later and how easy it is to transfer workflows, computing environments between machines, that's just like not possible to measure. So definitely worth sticking with it and like getting it to run. What we will see during the live session, there are actually certain tools, for example, a thing called NeuroDocker, that are very helpful with regard to reproducible creation and testing of complex images. And there they can also combine Python and container virtualization to bring these two things together, which is a fantastic thing to do. If you rebuild images during local testing, so if you try to get your compute environment to work and like really have the version you want to employ, if previous instances of the image will be untagged but not deleted. So we will just, for example, lose the latest tag to an untagged image, and then you have your latest image with the most recent changes, but the previous one is never going to be deleted. It's still there. And this could potentially become problematic with regard to storage clustering. So if you do it over and over again and changing layers, there might be some layers like that just clutter the storage, and so always make sure to check that out. If possible, your image should be shared publicly, for example, via Docker Hub, through providing a respective name and a tag and pushing them up there. This can, of course, potentially become problematic as old images with the same name and tag will be deleted again. Therefore, for example, if you use GitHub and Docker Hub, that is their integration, you can achieve automated builds and efficiently combine version control and virtualization, which might help address this problem. And you can specify certain build rules that will actually prevent that from ever happening, which is very good. So no matter if you went in the selfish dark path of non-existent reversibility and now want to join the light side of reproducible things, or you are always on the light side of the force and using it for the greater good. We hope that this lecture and session provided you with an overview that will enable you to further dive into and explore the respective tools and hopefully utilize virtualization sufficiently and efficiently within your research workflow. Starting with the work we're going to do during the live session, actually bring all these things into action and start going. And if we have the time and if you're up for it, we can definitely check what we can do for your specific projects you're currently working on. We can use the communication channels to do that. And remember that virtualization is great for sharing code, scripts, function pipelines with colleagues and everyone else without dependency issues. Also your future self, for example. The only dependency issue that you might face there is the virtualization software itself. But once you get that to run, having a very good encapsulated, nicely set up computing environment in a container that hopefully combines container and Python virtualization really makes a big difference. Because with that, you can automate large parts of your processing, you can rerun analysis with identical or change parameters. It's just all more easier to have a very good, solid workflow in terms of data inputs, output, processing stages. And this is important because we need to ensure reproducibility of results. Think back to the beginning in our problem statement. How much of a problem really these computing environments can pose to us because they are so complex with all of these different layers and aspects. And we need reproducibility because if everything diverges between computing environments, which one do we trust, right? It's an impossible choice to make, basically. And regarding the point we made here, rerunning analysis with identical and changed parameters, it's very important for the evaluation of soft and hardware parameters to just have a look at how these different settings might affect our results and what we can do to make it better, more reproducible and stable. And we have basically covered and talked about three main types of virtualization technologies, with kind of leaving virtual machines out of the game, which includes Python virtualization like vny and conda, and containers like Docker or Singularity, where they were situated along basically this outline ranging from bare metal to isolation of like in depth. So up here, like close to the application level, we had virtual envs and conda, so more Python virtualization things. And down here, we have our containers like Docker and Singularity. This is basically what we covered, leaving virtual machines out here because either you have worked with them before, they're a bit more known, but also they're less and less used because of the outline problems. We also talked about the different designs we have. It's 2x2 designs. First of all, for data and analysis, either being same or different, and all these different um, outcomes and data specifications, and what does it mean in terms of like what is when our data is the same or different in analysis or same or different. And there we focused on the reproducible aspect and introduced another 2x2 design where we define and characterize different virtualization techniques in terms of interaction style, graphical user interface based or command line interface based, and what they share or what is shared through them. That is either software or operating systems. To further provide maybe a more like focused summary in terms of like their pros and cons, we're just gonna go through these aspects maybe a bit more again. We're starting with Python virtualization. Their pros, they're more or less straightforward, mostly lightweight, of course depends on your environment that you're building, and should work cross-platform. The cons on the other side is they're restricted to Python and adjacent softwares. The later specifically if you use conda. The sharing across platform tends to be limited because, for example, going from a Linux-based system using Python virtualization there and then bringing that to Windows, depending on what you use, especially if there are adjacent things, not only pure Python virtualization, then things tend to get messy and maybe stop working. And there's no graphical user interface. Going now towards containers like Docker and Singularity. Their pros definitely share the entire operating system via dedicated infrastructures like Docker Hub and Singularity Hub, and you can create complex environments and even nicely integrate version control into that, which is a fantastic feature. They are comparably lightweight and fast to set up. Again, depends on the things and the environments you build, and they work cross-platform and even on HPC. With the cons being a tremendous steep learning curve, and they can definitely, if you not watch out and really test things and make sure, can reintroduce dependency through their current level virtualization and have no graphical user interface comparable to Python virtualization. Lastly, talking about virtual machines like VirtualBox and VMware, their pros are as containers, they share entire operating systems and can include complex environments, work cross-platform. They also have a graphical user interface, and that's, especially in the beginning, they seem to be easier to operate and work with. The cons are they are very heavy and slow because they need to emulate the entire software and hardware stack. They're mostly inefficient because just think about having your machine with 16 gigs of RAM and the virtual machine is taking 10 of them. You notice a significant drop in performance. They're also mostly not supported in HPC, and applying version control to them is definitely a tall order if possible at all. To provide some further reading, because we can only do so much in this very short amount of time, even though this is definitely, I guess, one of the longest modules, I provided some links that you can dive further into these topics. For example, understanding how conda and pip work a bit more in depth. We have a beginner-friendly intro to virtual machines and Docker, also a Docker intro from your Hack Week. A bit more about understanding images and, for example, some Singularity images you can check out. There is a one-day Docker workshop where all of these things we've talked about are discussed way more in depth, but as you can see, it's a one-day workshop, so it's a bit more time than we have here, but still the link is there and can go through it. And for anything reproducible, data, but also open communities, computing environments, software, I definitely recommend you check out the Turing Way, which has it's a Jupyter book. It's a great online resource, and has so many information and also further links. Definitely highly recommend it. Check it out. So, as a final statement, maybe if we talk about reproducible, scalable, and efficient research, we should definitely think about virtualization techniques, especially container technologies such as Docker and Singularity, because they can combine, for example, their own virtualization technologies with Python virtualization, but are a bit more lightweight than classical virtual machines, therefore combining the best of all worlds, basically. And since a while now, they are heavily featured and supported in different research workflows, and you can tell that it's getting more and more. Getting in on the ground floor on these things, starting early in your research projects and things you might want to do is definitely recommended. A huge time saver and will make your life, your entire research, uh, management, everything way easier. In the end, we have a few notes on Singularity, as mentioned before. So for the Compute Canada lecture, you might want to check these things out a bit more. That basically talk about differences between Docker and Singularity, especially focusing the different parts we went through in this lecture and we will go through during the live session. And with that, I would like to thank you for your attention. I hope you got at least some bits of information out of it. Definitely hope to see all of you during the live session. Have a great time there, actually getting all these things into action and start working with them. And yeah, please stay safe out there and have a good one.